Number 30 concerns finding the derivative of a function algebraically. The way we do that, we say that dy dx is the limit as delta x goes to 0 of the function evaluated at x plus delta x minus the function evaluated just at x divided by the delta x, consistent with the pictures that we saw before. And you know from your experience that when we do this simplification, the x plus delta x squared gives us x squared plus 2x delta x plus delta x squared. The x squareds cancel out. We end up with a limit of, actually it would be 2x delta x plus delta x all divided by delta x. The delta x's cancel out. I meant 2x delta x plus delta x squared divided by delta x. When we divide that out, we're going to end up with 2x plus delta x by steps that we're familiar with. And then the limit as delta x goes to 0 is just going to be 2x. Number 31 deals with interpretation of the derivative, especially with the units of dy dx. To interpret a derivative, we want to interpret what the units mean. So the units of dy dx, of course, the change of y is going to be in y units, the change of x is going to be in x units. And when we do dy over dx, we divide the change in y by the change in x. This tells us what the change is in y per unit of change in x. For example, if y is in meters of depth and x is time in seconds, then we get the number of meters of depth change per unit of time, which is seconds. Depth change per time, centimeters per second. Numbers 32 and 33 deal with the calculation of the second derivative and the interpretation in various forms. If we have a function, we could have three t values, t0, t0 plus delta t, t0 plus 2 delta t. These would just be three typical values of the time. We would have three values of y, which I haven't filled in here, but there are three numbers here, just like there are three numbers here. For each time interval from t0 to t0 plus delta t and t0 plus delta t to t0 plus 2 delta t, we have a midpoint. The midpoint between here and here is t0 plus 1/2 delta t. Between here and here, it's t0 plus 1.5 delta t, or 3/2 delta t. To that midpoint, we associate the delta y over delta t for that interval. So in this first interval, we would have two y values, so we'd calculate our delta y. We'd have two t values, we'd calculate our delta t, we'd divide them, and that would give us an approximation of the derivative at the midpoint. It's not an exact value, it's only an approximate value, and we associate it at first approximation with the midpoint of the interval. Then we do the same for this interval. We have our two times. Difference in time, of course, is delta t. We have our two y's. We divide the difference of the two y's, or the change in y, by the change delta t, and we get another approximation of the derivative, another delta y over delta t, which we associate with the midpoint of this interval. Then, to calculate a second derivative, we go the midpoint of our two times here. That's going to, of course, be t0 plus delta t, the middle time. We have associated with this midpoint a derivative, and associated with this midpoint a derivative. The midpoint of the midpoints is t0 plus delta t. We can calculate the difference of the two derivatives. That's a delta of f prime, the change in the derivative, delta f prime. And divide that by our delta t between these two. So we have the change of derivative between these two f primes and the change in t between these two clock times. And that's going to give us an approximation of the second derivative, the rate at which the derivative changes. This is how we can interpret the second derivative. You also recall that with the trapezoidal approximation graph, f double prime is the rate of slope change, the average rate of slope change. Remember that we have a slope on one interval, which would correspond to the f prime for this first interval here, associated with the midpoint of the interval, and a similar slope in the second interval associated with the midpoint We take the difference of those slopes, and the time interval will be just our delta t. We divide the difference by the delta t, we get f double prime. When f double prime is positive, our graph tends to be concave up. When it's negative, it tends to be concave down, because a positive second derivative means an increasing derivative or an increasing slope. Negative second derivative, decreasing derivative, or decreasing slope.